When we think of nuclear fusion, we usually picture massive, multi-billion-dollar magnetic cages holding superheated plasma. But there is a completely different approach that aims to trigger fusion inside a simple cup of liquid, right at room temperature. The trick relies on a simple substitution. If you take a standard hydrogen atom and replace its electron with a heavier subatomic particle, the entire atom physically shrinks. That replacement particle is called a muon. It carries the exact same charge as an electron, but it is 207 times heavier. Because of that extra mass, the muon is pulled into a dramatically tighter orbit around nuclear center. This shrinking effect is so extreme that it drags neighboring atomic nuclei close enough to tunnel past their natural repulsion. They crash into each other and fuse, scaling a reaction that normally requires the core of a star down to the size of a desk. There is a catch. Muons don't just float around waiting to be used. Producing them requires a particle accelerator, and creating just one muon costs about 5 billion electron volts of energy. This chart shows our massive energy deficit. Next to a 5 billion electron volt cost, a single fusion yields only 17.6 million. To pay off this debt and generate net energy, one muon must stick around and catalyze roughly 450 fusions. And that muon is on a very strict timer. It has a natural lifespan of exactly 2.2 microseconds before it decays and disappears completely. Success becomes a high-speed race against time, trapping a single particle in a continuous loop and force cycling it hundreds of times before its microsecond timer runs out. To build that loop, physicists shoot a fast-moving muon into a liquid mixture of two heavy hydrogen isotopes, deuterium and tritium. The cycle starts with a swap. The incoming muon knocks a standard electron away from a tritium atom and takes its place, instantly shrinking the atom's boundaries. Because this newly formed muonic atom is now incredibly small and neutral, it easily slips inside the electron cloud of a neighboring deuterium molecule and pulls the second nucleus in tight. Now the physics rely on the Westman resonance. The energy of these trapped atoms perfectly matches the natural vibrational energy of the host molecule they are sitting inside. This perfect match forces the two nuclei to merge. They fuse, release their energy, and violently kick the muon back out, leaving it free to find another atom and start the cycle again. We know this cycle works because physicists have seen it in action. In 1956, Luis Alvarez observed these sharp, jagged tracks in a bubble chamber, proving that a single muon could bind, drift, and then shoot off again after forcing a fusion event. The Westman resonance takes what should be a sluggish physical process and turns it into a blindingly fast loop, providing the only realistic chance for a muon to hit its 450 cycle quota. When this concept was first mapped out, early models assumed the cycle would be too slow, predicting a muon might manage only 1 or 2 fusions before decaying. But by leveraging resonance, modern experiments have accelerated the loop to extreme speeds. Currently, physicists have successfully pushed a single muon to catalyze about 150 fusion reactions. Hitting 150 cycles changes the fundamental math. It demonstrates that the 450 cycle break-even point is a physical possibility that we can engineer toward. To successfully get from 150 to 450, researchers have to solve a fatal flaw in the cycle known as alpha sticking. When deuterium and tritium fuse, they create a helium nucleus or an alpha particle. About 0.5% of the time, the muon fails to eject during the blast and instead permanently binds to that helium waste. This sticky trap locks away the catalyst, halting the loop and preventing current systems from reaching the energy break-even limit. Even with this specific leak, the process remains useful. Every fusion event in that 150 cycle run generates a high-energy neutron. Scientists are already using these intense muon-powered neutron beams to safely break down toxic, high-level radioactive waste. Even if it isn't powering a city today, mastering the leaky 150 cycle loop has provided a specialized method for neutralizing hazardous nuclear waste. To fix the loop itself, researchers are testing a theoretical solution called in-flight fusion. Instead of a gentle collision, this method forces the molecule into an excited state, triggering a much more violent nuclear merger. The force from this reaction ejects the muon while it is still moving at high speed, giving it enough kinetic energy to blast straight through the sticky helium trap and stay in the loop. This cycle requires shrinking the atom, tuning resonance to speed it up, and finally, engineering a high-speed bypass around the atomic ash. If physicists can perfect this bypass and close the leak, they will transform a simple cup of water into a self-sustaining, localized power source.